And the first talk today is going to be on work in progress, labeled Union Find for Constraint Factorization by Matthieu Lemerre and Dorian Lesbre.
Yeah, thanks for the introduction. So this is a work in progress paper with my PhD student Dorian. And so what is this talk about? It's about a new family of very cheap relational abstract domain. So earlier Michael did a nice introduction to the topic where you have non-relational domains which are very inexpensive, and you have these expensive domains like polyhedra, which are very expensive, but you have lots of relation. And in the middle, you have these weakly relational abstract domains, which are less expensive, but you have fewer relations. But actually, they are still very expensive because you have a quadratic costs in storage and cubic costs in computing some operations. And so we want a cheaper abstract domain that doesn't need all these mitigation strategies, things like that. So the idea is to have a very cheap domain which is still relational, so it can be always on, and you don't need to worry about having it in your base abstraction. And so what this relational domain can do is to compute binary relations between variables. And it can compute relations like y equals a times x plus b, so affine relations, or with relations like y equals x XOR some constants, or with some constant rotation, or even with some permutation. Actually, any kind of invertible relation expressive as an invertible function will be representable in our domain. So we think there are two main applications of this domain. The first is natural, is to increase the precision of your abstraction by having more relations between variables than if you had just a non-relational domain. And the second application is what we call constraint factorization. Is the idea of you can make existing domains more efficient by grouping variables together, and the idea is that you will have fewer variables in your abstract domains, and that way your abstract domain will be more efficient. So this was a summary. Now I want to explain why are these weakly relational domains. They are already very costly, and I think one of the main problems is an operation which is called constraint propagation or reduction. So the idea of constraint propagation is to improve the precision of your abstract domain without having to change the concretization, the set of values that it represents. So I will be using as an instance the zone abstract domain, so relation of the types y minus x is in some interval, and I will be representing them as a pair of variables mapping to some abstraction of relation. So here I will be using an interval. So for each pair of variable, I'm using an interval. So for instance, this represents that between x and y, you have the interval 1 or 2. So one kind of constraint propagation can you apply? The first is apply reflexive closure. So you know that the relation between x and x is always 0. So you can refine your abstraction thanks to this knowledge. The second one is symmetry. So if you know that y minus x is between 1 and 2, then x minus 1 is between minus 2 and minus 1. And so you can propagate like this. The operation done for this is the inverse of the relation. In the case of intervals, it will be just the negation. And the last operation that you can use is transitivity. So if you know that y minus x is between 1 and 2, if you know that z minus y is between 3 and 5, then you know that z minus x is between 4 and 7. Okay, so if we look at what we get here, what is the storage cost of all this is quadratic in the number of variables. So if I have 3 variables, I need at least 9 relations between all 3 variables. And the computation cost is basically the transitive closure of a relation. It is cubic. So those are actually very expensive. And the worst is that you always have to do this full constraint propagation. So you always have to do a transitive closure before joining. And this is a general result in abstract interpretation. If you don't do that, you will lose precision. So you cannot avoid doing this constraint propagation. So the idea that we get is, okay, maybe we can make the domain more efficient by doing the contrary of constraint propagation, which we'll be calling constraint elimination. So the idea is that we want to remove some relations if it can be efficiently recovered by constraint propagation. So, for instance, we can do reflexive constraint elimination. So you don't actually need to store the relation between y and y because you will not be able to have something more precise than the 0,0 interval. So you don't need to store this information. It is implicit in your set of constraints. You don't need to store both the relation between y and z and the relation between z and y. You can infer one from the other. So actually, you can divide the cost by 2 by storing only one of those two relations. It works particularly well because the negation of intervals is an exact operation in the sense of a forward complete operation. The real problem is elimination of transitive constraints. So if you wanted to remove the relation between x and y, you could do that, but it means that you would have to compute all the possible paths between x and y, compute what is the relation on each of these paths, then do the intersection of all these values, and then take the best one, and then you could do that every time you wanted to know the value between x and y. So obviously it will be very, very expensive, and you don't want to do that. So that's why we will be cheating here, and we will be using an assumption. And the assumption is that the value that you will be computing on every path will already be the same. So if you have this assumption, then you don't need to compute the value of on every path. You only need to compute the value on one path. And so basically, all you need now is that all of your variables are linked to the other. So you only need a spanning tree of the graph to store the set of relations. And now if you want to store to compute the relation between x and z, then it's very easy. You just have to compute this relation between x and y, and then the relation between z and y, and compose that. So this becomes now very inexpensive. So this explains how our abstract domain works. So now it will not work for the zone abstract domain because the zone abstract domain with intervals on relations doesn't have this property. But if you restrict the zone abstract domain to have only constant offsets between two pairs of variables like this, then it will work. So for instance, if you know that the relation between x and y is plus 2, and between y and z is plus 3, then you know that the relation between x and z is minus 1. So this is the general idea of what our domain computes. And to implement that, we will be using a data structure which we call label union find data structure. So as you saw here, basically the set of relations represent a tree. It will be a rooted tree, so a tree where each element points to its parent. And we will be using that. But before, I want to say that the natural settings in which this restriction that I propose, the fact that the value on every path is the same, it will naturally form a group structure. So for instance, you will have the law of associativity, because if I have this diagram here with many relations, then basically if I go from this path to x to z, then followed by t, or if I do this one followed by this, those must be equals. And if you look at that, it implies that the composition association is associative. You will also have neutral elements because the path from x to y is the same from the path from x to y to z to y. And so the composition between L2 and S3 will be a right neutral element for the composition here. And you have neutral elements, but you also have inverse elements, because if this is a neutral element and this is a neutral element, then basically L2 is the inverse of L3. So associativity, neutral elements, and inverse elements mean that we have a group structure. So this brings me to this label union-find data structure. So it's actually a union-find data structure. So if you don't know what union-find is, it's just a tree where every node is pointing to its parent. But the difference is that on this link from each element to its parent, we will have a label like this. And we ask that all the labels obey the group properties. So we need an identity relation on labels, and the possibility of inversion of every label, the possibility of composing any pair of labels. And we want all these operations to obey a loop of group. And we have three main operations which are derived from the union-find operation. So the first is find. So basically, we take an element n, and we want to find both the representative element, which is the root of the tree, but also the relation that you have between this element and the root. So the relation here will be the composition between two from LM, then LR. And moreover, we'll be updating the tree. This is an operation which is called path compression to make a shorter link from the element to the root. Another operation is the add relation operation, which corresponds to the union is a union find. So the idea is that if we say that we learned that there is a relation between n and m, and this relation has label L, then we will be adding a new relation between the roots. So we compute the root of n, which is Rn, the root of m, which is Rm, and we add this link, which is basically inverse of Ln, then L, that Lm between Rn and Rm. And the last relation, the last operation that we need is get relation. So if we want to know if n and m are related, then we compute the root of n, the root of m, and if they are equal, we know that the relation between n and m is ln followed by the inverse of lm. So all those operations are very efficient. The union-find data structure is one of the most efficient data structure in computer science. It's all operations are almost equal, are almost constant. Now we did some study of what does it mean for an abstract relation to be a group. So basically, there is something that we want for our abstract relation is that all the operations are sound. So the abstract composition is an sound abstraction of the concrete composition of relations. Same for inversion and same for identity. And basically what we found is if you have both the fact that your abstract relations are sound and that they follow the group laws, then it means that all relations must be injective function. So for instance, the zone constraint here is not an injective function, because if I precisely know the value of x, and I know that y is x plus some value in some intervals, then I cannot deduce the value of y. So it's not an injective function. Whereas if I have just the relation y equals x plus b, then if I know the value of x, I will retrieve the value of y, and vice versa. So this is an injective function, and that means that it can be encoded in our abstract domain. Another interesting property. So actually, I said it was injective function. It's actually injective function between equivalent classes. So it means that you can actually take some information about variable x, some information about y. If you can relate both of this information using injective transformation, then you can also encode it in our domain. And another interesting property is that if you don't do anything stupid, your lattice will be flat. So basically, either you will have no relation, you will have bottom, so incompatible relations, or you don't know the relation between two variables, or the relation will be precisely one invertible function. So once you know that, it's also the contrary. Whenever you have an invertible function, you can encode it in our domain. So we thought, what can we use as a relation in our domain? So one very useful relation is this affine equality, so two variables pair equality. so of the form y equals ax plus c. So this kind of relation happens a lot in our programs, of course. An interesting case is affine relations in modular arithmetics. So if you multiply by 2 in modular arithmetics, it's basically equivalent to doing a shift. So it means that you are losing some information, which is information about the top bits of the old value. So this is not an injective function, so you cannot represent it in our domain. But if you take an odd number, because an odd number will be primed with 2 power something, then it means that it can be represented in our domain. So we can represent ax plus b in modular arithmetics, but only if a is an odd variable. Another interesting property is to take, so if you do a XOR with a constant, then it can be reverted if you XOR again with the same constant. So this is an invertible operation. If you do some kind of rotation, it's also an invertible transformation. So it's also possible. Actually, if you do any kind of permutation, you can encode it in our domain. And if you look at it very closely, the combination of XOR and rotation means that you can also encode shifts if you know what are the values of the bits that have been shifted. So it seems weird, but actually there are lots of cases where we can use this relation. And yeah, there are many other relations that we could think of. Okay, so now I've explained all the kind of relations that we can encode using these new abstract domains. And I want to explain some of the applications that we have been starting to study. And one is a reduced product with a standard and SSA-based non-relational domain. So I will first explain what is an SSA-based non-relational domain. It's something that we published this year at PLDI. So basically, we have an analysis which builds a set of terms, which we call symbolic expressions. And our numerical state is a mapping from each symbolic expression to some interval. So for instance, we know that variable x has value corresponds to the term alpha 2 plus 7, and alpha 2 plus 7 is mapped to this interval between 7 and 11. And we show that if you do that, you are always more precise than a standard non-numerical domain. And why it's more precise? Because it's actually not really non-relational. You actually have some relations between your variables, and the relations are given by the relations that you have between all the terms. So what we can do is to apply some constraint propagation between all of the subterms. For instance, if we know that this condition is true, it means that this variable is below 11, which implies that alpha 2 plus 7 is below 10, which implies that alpha 2 is below 3, which implies that 2 times alpha 2 is smaller than 6. So this works well. So how can the labeled union fine domains that I've presented be useful in this context? Well, the first thing that we could think of is that you will be able to find new relations that we could not represent before. So for instance, we can represent a relation between alpha 1 and alpha 2. Say, okay, maybe we know that alpha 1 is 3 times alpha 2 plus 2. And so we can propagate more information, because if we know that alpha 2 is in this interval, it means that this alpha 1 is in this interval. So we learn something, we are more precise. But another interesting application is what we call constraint factorization. So the idea is to say, okay, actually all of these variables are grouped using this label union fine data structure. It means that, normal union fine are used to represent equivalence class. So we have some kind of extension of a notion of equivalence class, and where all the variables that are related, we can group them. And instead of storing the interval for each of these terms, we represent only an interval for the representative element of the term. And it's interesting because when we do constraint factorization, instead of studying all the possible relations that you have between any pairs of the variables here, we update the interval for the root once, and then all of the other relations are automatically updated. And so we save a lot of time spent doing this constraint propagation. So there are some conditions for this to work. And the condition is that the operation that is represented here, the injective transformation, must be forward complete with regard to the non-relational abstraction. So +7 is complete compared to the interval abstraction here. So this works well. So yeah, to conclude, this is where we are currently. What we have done, we have defined this new kind of data structure, the label union find. So maybe it's not completely new because you said something that may be similar, this quantitative union find. It will be interesting to find out the relations between both. So what is this label union find? Is a union find where you have labels which are elements of a group. We have a new family of abstract domains, which is based on this labeled union find data structure, using abstract relations as labels. And as we saw, it can represent many injective functions between equivalence classes. And we saw that there are two kinds of use cases. The first is to use the domain as is, just to increase precision of non-relational domain. So if you have only non-relational domain, it will be very useful. But if you have relational domains, when we think that this domain can still be useful as a way of having fewer domains, because you can group domains together to have fewer variables. So for instance, if you have octagons and you have this constant of that domain, then instead of representing the relation between x, y, and z, then maybe you know that y equals x plus in some constant, and you can remove y from the octagon representation. And the difficulty then is that you have to be careful when you do the join, because you have to do this constraint propagation on the fly, which makes the algorithm a bit more complicated. So I think there are a variety of applications of this domain, not only in abstract interpretation, but also in constraint propagation or in decision procedure. This could be useful as a cheap way of representing some information. But of course, in abstract interpretation, it's harder because we have this join operation, and actually just joining the union find is quite complicated. So we will be interested in exploring this constraint factorization in a variety of domains, because it could work for octagons, polyhedra, linear equalities, two variable par inequality, things like that. Because a subset of the domain can be represented by our labeled union find domain. And we are working on a robust open source implementation on our codex analyzer. And we want to do some benchmark and evaluation before having a full paper. So thanks for your attention, and I will be happy to take any question.
Are there questions for Matthieu?
Thanks for your talk. Have you looked into actual sort of C code examples? I'm imagining when you have all these different abstract domains, you can get really sophisticated like analysis of integers. Are there like some examples that motivated this? Because it seems like when I think how a lot of people write these, the programs are often not that complex. So, but maybe happy to be proven wrong here.
There are many examples where it can be useful. For instance, if you have often you have some like a while loop where you increment a counter and you also increment in sync a pointer. So you will have a relation between the pointer offset and the counter. And so this is exactly the kind of relation that you will be able to represent here. So a relation between the two of these variables. For now, we have already checked that it does not make the analysis complexity more go higher. So it's cheap, and in some cases it gains precision. But actually, to fully take advantage of this, we need to be very careful in the way that we do our reduce projects between the non-relational domain and in this domain. And this is not fully as fully precise as we would want. So we gained already some precision in some case, but yeah, we don't have the full numbers for that yet, so that's why it's still work in progress.
All right, I think we have time for one or two more questions. Okay, then maybe I have one. So you've said you have already experimented at least a little bit with it, and you said the overhead is at least not huge. Do you see an overhead at all, or is it sort of so cheap or that it basically pays for itself?
Yeah, I think from what we saw, it was less than 10% overhead, so
Okay.
very, very, very cheap. Something that I did not mention is so we are in these particular settings of this SSC-based analysis. So what you have here is that the relation between different terms is flow insensitive, and because it's flow insensitive, you can represent it in a union find, which is the imperative union find, the standard one when you can do path compression and things like that. This is what we have implemented yet. But we would also like to have some flow-sensitive labeled union find data structure. But for this, we need to implement a join algorithm, and the algorithm is a bit more involved. And this is something that we don't have yet. So, yeah, we don't know for that. Probably we'll have more precision gain when we have this flow-sensitive union find, but we don't have it yet.
All right, thanks. And then one last question right here.
So thank you for your talk. So how it compares with the E-graphs, which are used in SMT solving and so on? Because you have these nodes where you apply a function and so on. So you'll try to generalize to some properties about symbolic computation on these graphs and so on. But could you explode more such structures in a symbolic way?
So E-graph is basically you have this subterm relationship, and then you have equalities, but you also have to perform the congruence closure. So we don't have this congruence closure, but our notion of equivalence is stronger because we have this injective function in the middle. So I think both are complementary, and actually it would be very interesting for us. It's something that we would like to go to, is to use also E-graphs instead of just terms in our abstract domain. But I think they're related but complementary. Yeah.
All right, then let's thank Matthieu one more time.
Yeah, thank you.